Hello, this is Andrei Kharchenko, and I would like to introduce my message encryptor tool. So here's the contents of my presentation. Page 3 is going to be the credits. Page 4 is the problem statement. Page 5 is the project goals. Pages 6 and 7 are the technicalities of my tool. Pages 8 through 10 are the challenges of my tool. Pages 11 through 13 is the development. Pages 14 through 16 is the implementation. Page 17 is other possible uses of the source code. And page 18 is the conclusion. This tool was developed by me. The language used is C++. The IDE used is code blocks. The executable size is about 1 megabyte. The size of the source code file is 9 kilobytes and it's 312 lines. What the executable does is it encrypts and decrypts words or characters written in Latin alphabet in 3 ways: double key encryption, modular shift, and Caesarean shift. So here are some real-world problems that can be solved with this app. Currently, a war rages on in Ukraine. Ukrainians could use my software for more secure communications between each other. Here are the project goals. Number 1 is to explore and study various encryption methods that exist, mainly Caesarean, modular shift, and double key encryption. Number 2 is to practice coding. Number 3 is to practice optimizing code so that it is most efficient and takes up less space. Number 4 is practice arranging the interface in a way that is easy to use. Here is why I chose the platform and the language that I used for development. The advantages of using C++ with CodeBlocks IDE are as follows. I have previous experience with C++. C++ is an object-oriented language. There are a lot of libraries available for a C++ project. CodeBlocks IDE is specifically designed for C++ projects. It runs on my operating system. I have experience with it. It has an integrated debugger and it is free to use. Here are the technicalities of my project. So basically how it works, what it does. For encryption, step 1 is to translate every character to be encrypted in an integer. Step 2 is perform mathematical operations with the integers, so it can be a shift, a Caesarean shift, it can be a modular shift, or it can be double key encryption. Step 3, translate the changed integers back into characters. And for decryption, it is step 1, translate characters to be decrypted into integers. Step 2, perform mathematical operations with the integers. Step 3, translate the changed integers back into characters, outputting the decrypted text. And exceptions have been made for the key encryption part of this tool. It outputs integers instead of characters because there aren't enough characters to cover all the integers after 26. Here begin the challenges of my tool. So first challenge is translating the value of the number into letters and back. It may seem easy to translate A into 1 and back, but it's actually pretty difficult, especially when you have to shift your values up or down by a certain number. This was my first attempt at linking the character values to integer values. As you can see here, these two images, it may be hard to see, but it's a function int char to int, returning a type int, and there is a function int to char, returning a type char. So the char to int function is supposed to return an integer for a character, and the int to char function is supposed to return a character for an integer. As you can see, it is very complicated. There's many lines of code here, and I fixed this. Eventually, I optimized my code to be shorter and more efficient, which I will show on slide 11. Another challenge that arose is dealing with values above 26. For example, getting a value of 100 after public key encryption. How does one translate that into letter format? The eventual solution I came up with to this problem is to just give out a list of integer values that mean to represent every letter in the string to be translated. One interesting quirk we can observe is that for 2 different executions, you can see execution 1 enter message friend and execution 2 enter message AAA, the public keys used in the encryption are identical. It's the exact same keys. This is a problem and it occurs because computers rely on preset algorithms to generate random numbers, so they're not really random at all. Here's another challenge. This challenge is about generating private and public keys. So at first I used a set of 10 pairs for encryption keys. I couldn't fit the whole screenshot here because it would be too much space. But this is 61, 53. This is one of the 10 pairs. Later I changed my code to actually generate public and private keys randomly. Once again in quotes, because it's not random at all and predetermined by computer. Now here is an optimized int to char and char to int function. So char to int function returns an integer for a character, and int to char returns a character for an integer. So if you look at the int to char function on the right, you will see that there is an exception for if the integer is equal to -2 or -1 or 0, and the reason it's there, it actually serves a purpose when decrypting messages using the Caesarian method, because the Caesarian method shifts the decryption with the Caesarian method shifts the values by -3, which means that the lowest value a character may have attached to it is -2 instead of 1. So that's why there is a if n is equal to -2 return z. My public key encryption algorithm uses two public keys, n and e, to encrypt a message. Unlike my other encryption functions featured in this app, this one does not return anything. You can see it is void. The return type for this function is void. Instead, it prints the encrypted integers, each integer representing a letter. The reason this function does not return a string, unlike every other function in my app, is because the integer values obtained through this algorithm far surpass the number of characters we have that could represent them. For example, this is a message I entered, DEFG, and this is what it encrypted to. 64, 126, 216, 343. Here we see that it is impossible to represent any of these integers with characters in the Latin alphabet. There's just not enough of them. Here is the algorithm that my app uses for modular shift encryption. So it uses the equation E is equal to 7 times T plus 7 mod 26 plus 1 to encrypt messages with the modular shift. E is the encrypted character, so E is the output, and T is the readable character. And for decryption, my app uses the reverse of that, which is T is equal to in quotations E minus 1 times 15 mod 26 minus 1. This is obtained via the extended Euclidean algorithm, where x is congruent to 15 mod 26, and in other words, x differs from a multiple of 26 by a value of 15. So here's some example implementations of my tool. This is an example of implementation of Caesarian shift with my tool. So if you want to use Caesarian shift to encrypt, you press T. If you want to use modular expansion to encrypt, you press R. If you want to encrypt via public key encryption, press E. And to decrypt with public key encryption, you press D. To decrypt with modular expansion, you press F. To decrypt with Caesarian, you press G. And you do this after every encryption or decryption. It just comes back to main. It's very easy to use, actually. Very handy. So, an example of implementation of Caesarian shift. Here I entered the message missile Kherson, and here's the encrypted message. I'm not going to read that, it's impossible to read. But when you decrypt that and you enter this message, you get decrypted message is missile Kherson. So you can encrypt and decrypt back and forth very easily with the Caesarian shift. Although Caesarian shift is pretty easy to implement through code, it is not a very effective method of encrypting information because it can be easily broken. So here is an example of implementation of modular shift. The modular shift message, enter message Tank Mykolaiv, and here is the encrypted message. Once again, I cannot really pronounce that. I cannot read that. And then we enter the encrypted message and decrypt it, and we get the same Tank Mykolaiv. Modular shift is a bit more reliable in securing information. However, it is still not secure enough for super important information like bank accounts and anything relating to finances. Here is an example of implementation of double key encryption. So here I show you me encrypting with a public key. The message is victory, and we get some numbers for it. We get the V is 10K 647, I is 729, C is 27, T is 8K. So you can kind of follow what all the numbers are. We get an encryption, but we cannot really decrypt it back. We cannot decrypt the message that we just encrypted, which is a problem. My tool effectively encrypts using double key encryption, but cannot decrypt messages. I will be posting the code to GitHub though, so other users may improve it and resolve this issue. Here is the GitHub link. It is also going to be in the description of this video. The code could be used by other developers and improved upon. Most importantly, improvements could be made toward accurately decrypting messages that were encrypted with double key encryption method. In conclusion, this tool has a lot of potential uses in warfare or police work. However, I do not see any way it could compete, even with the help of others on GitHub, with the encryption software used by big tech such as GPG or TLS. Really, this was just a cool project for me to practice coding on.